Okay, so we just talked about the prisoner problem. So in the prisoner problem, there's a guard, prisoners, right, and boxes. And they put the numbers in the boxes, and the prisoners have to go in one at a time. They get 2 tries to find their number. If they all find their number, they're released. Okay, and the hint I gave you for the solution was that that we had to look at the permutation group S4. Okay, so what is S4? What does it have to do with this? So S4 is the permutation group, or the symmetric group on 4 elements. Okay, so it is the number of ways to scramble 4 things. So this is all scramblings of the set 1, 2, 3, 4. So all the bijections from 1, 2, 3, 4 to itself. So this is a symmetric group on 4 letters. How many elements does it have? Well, the number of elements of this group, right, is 4 factorial. Right? That is, so there's 4. So you have to choose where 1 gets sent. There's 4 possible options. After that, you need to decide where 2 gets sent. So after we decide where 1 gets sent, there's 2 options for that. Then we need to decide where 3 gets sent, right? Then there's 3 options for 2. And then there's 2 options for 3 and 1 option for 4. So that's 4 times 3 times 2 times 1. And that is, okay, so 12 times 2, that is 24. Okay, so there are 24 ways in which to scramble the letters I, or 1, 2, 3, and 4, right? So you can permute them in a bunch of different ways. And there's a thing called cycle notation, right? So there's in cycle notation, right? So every permutation can be written as a product of disjoint cycles. And so it either has the form, A, B, C, D. So any permutation can be written like this, or it became written as A, B, C, D. So these are letters 1, 2, 3, 4, right? Or it can be written as A, B, or it can be written as A, B, C. Okay? So this one sends A to B, B to C, C to D, right? And then D back to A. Okay? So so how many different ways are there to do this, right? So let's kind of just check that these are all the 24 types. Okay? So I have to pick a letter for A, B, C, D, right? But this thing, okay, so then there's it seems like that there's 4 factorial options, right? So there's 4 factorial, 4 times 3 times 2 times 1 of these, right? But then they're all the same if I were to rotate this around. So A, B, C, D, right? That would be the same permutation as B, C, D, A, or C, D, A, B, right? So if I started somewhere later in this cycle, it would denote the same permutation, because it would still be A that goes to B, B goes to C, C goes to D, etc. So of these, we've overcounted by 4. We did 4 times as many. Okay. So the number of these of this type is 6. Okay. How many are there of this type, right? Where A goes to B and B goes to C. So like we could have 1 goes to 2 and 3 goes to 4. And then 2 goes to 1 and 4 goes to 3. So these 2 things just get interchanged, and these 2 get interchanged. Okay? Well, it looks like we have 4 choices again. Okay? But now, so we can permute these 2. So the permutation, the cycle AB is the same thing as the cycle BA. Right? A goes to B and B goes to A. Same thing. So we're overcounting here and we're overcounting here. So that's 2 times 2. But then we're also overcounting because these 2 permutations commute, right? So the permutation that just permutes A and B and does nothing to C and D commutes with the permutation that flips C and D and does nothing to A and B. Okay, so we're also overcounting by 2 there, right? And so what is this number? So this is just 3. Okay, so how many of these are there? Okay, so that covers these permutations. These are what are called the transitive permutations. Or sorry, not the transitive. So these are the permutations without any fixed points. So there's no element of 1, 2, 3, 4 that doesn't get moved. This one here, however, this one, which is one of the factors of this one, it would just AB. Well, whatever C and D are, they're going to be fixed by this thing. And so this thing just has 4 times 3 options, right? And then we're overcounting by 2. So this thing will be 6. There'll be 6 of these. Okay, how about this one? So this is the same thing, right? So this is a 3 cycle, and then one of the elements gets fixed. So this could be like 1 goes to 2, 2 goes to 3, 3 goes to 1, right? And then it just cycles these elements, and then this thing stays fixed. Or you could do it with 2, 3, 4, whatever. You just pick a subset of 3 of these, and then you pick a cycle, right? And then the other one stays fixed. Okay? So how many options? There's 4 times 3 times 2. But then we're overcounting by 3 because 3 things are the same permutation. Okay? So now this is 8 elements. Okay? And then there's of course like the trivial element here, 1, right? And there's only one of these, the unique identity here. Okay, so this is so let's check that this makes sense. So I tried to count all the elements of S4 or all the types, right? Okay, so let's check this. Let's just do a sanity check here. If these are all the elements, right? Then it turns out that okay, so if these are all the elements, and they should add to 24. Okay, so we need 6 plus 3 plus 6 plus 8 plus 1, right? So what does that equal to? Okay, so so this thing here, this is 4, and 4 plus, so that's 10, right? So 4 plus 6 is 10. Okay, and then this is 16, and then 16 plus 8 is 24. Okay, so all the elements, it turns out that we have counted all the elements here, right? And if we wanted to be like super explicit, right? So this one here, so if we wanted to be super explicit, what are all the elements of this type? So all the permutations of this type are, okay, so I wanted to do the really small one. So there's 1, 2, 3, 4. Okay, there is 1, 3. Okay, 1, 3, 2, 4. And then I guess there's 1, 4, 1, 4, 2, 3. Right? So there's these 3 elements here. Those are the 3 permutations. And then I guess you can kind of normalize them. So we said we could flip these around. So this would be the same thing as 2, 1, 3, 4. Okay? Yeah. Okay. So these are the elements. We could. What was I going to say about normalizing? You can always arrange so that you put the smallest one first. Say. Okay. Once you have more than 3, they're gonna get out of order. But for this particular one, you can do it that way. Okay. So all right. So back to reality here. We were talking about the prisoner problem. Okay. And so what happens is that this warden is really choosing an element of some permutation of S4, okay? And so what he's doing is he's scrambling these 4, these people, right? Their numbers, right? And the game is to undo the permutation, right? So what they need to do is they need to somehow get back to their number, okay? And all right, and so the winning strategy is as follows, right? 1 goes in, and so this one turns out to be a losing strategy. But let's look at the permutation here. Okay, so 1 goes to 3. Okay, 3 goes to 4. Okay, 4 goes to 2. And then 2 goes to 1. So this is a 4 cycle. And this turns out to be a losing permutation, right? For the strategy. But let me tell you what the strategy is. The strategy is 1 goes to box 1 and opens it up and finds 3. Then they go to box 3 and they open it up and it's 4. Okay, so they lose. The same thing. They're all going to lose now because it's this type of cycle. So 2 goes to box 2. It opens it up. It finds 1, and then it goes to 1 and finds 3. So they lose. 3 goes to box 3. It would open up. It would find 4. Then it would go to 4, open it up, and hope to find 3, but it's actually 2, right? 4 would go there, and it would open up box 4, find 2, and then go to box 2 and find 1. Okay, so for this particular cycle, their strategy would lose, where they kind of just chase their number, right? So they go to their box, they look at this number, then they go to this box and open it up. Okay, so what would work is it would work if so this strategy works. Okay, so let me grab another marker. So this strategy works. This one might be dead too, but let's find out. Okay, so for cycles of type, for these cycles, for A, B, C, Ds, right? Because here, right, if it was okay, so let's pick one like this. And then let me do another one. It works for this one as well. Okay? Okay, so it works for these two things. So this contributes, this contributed, there's 6 of these. And there's 3 of these. We counted them. 3 of these, and then there are 6 of these. Okay? And this gives a total of 9. So the number of permutations, so the number of winning permutations, so this is greater than or equal to 9. And so this means that the chances of winning so this is greater than 9 over 24, right? Which is bigger than 8 over 24, which is bigger than 1/3. So this is about a 33% chance of winning. So they at least have a 33% chance of winning. So what would a winning permutation? So I'm saying that if we have, so let's pick one of these permutations that was winning. So say it's one of this type, okay? So this is a winner, right? So then the boxes would be like so, right? It would be like, so let me write the boxes here. Okay. Okay, so here's person 1, here's person 2, here's person 3, here's person 4. Okay, so here's box 1, here's box 2. Okay, let me make the little room here. I don't know, the doors opens on the other side now. Okay, so here's the room. And then, so what did we want? We wanted to permute it according to, say, the 1, 2, 3, 4. Okay, so 1 goes to 2. Okay, and then this one was this permutation, and then these 2 were flipped, right? This is one of the 9 winning permutations. Okay, so what would happen is 1 would come in. It would go to box 1. They'd find 2. They'd go to box 2. They'd find 1, and they would win. 2 would come in. 2 would go in. They'd go to box 2. They'd find 1. They'd go to 1. Then they'd go to 2, and they would win. 3 would come in, right? 3 would go to box 3, go to 4. Then they go to 4. Then they go to 3, and they would win, right? 4 would go in. They would go to box 4, right? They'd open it. They'd find 3. They'd go to box 3, find 4, and then they would win. Okay, so this is a winning strategy for 1/3 of the permutations, and you're assuming that that they're not the warden here does not have an affinity for cyclic permutations, right? So you're assuming that the permutation is genuinely random, and if it's genuinely random, right, then you'll have 9 possibilities of winning with this strategy, which gives you a 30% chance of winning, which is much better than 1/16. Okay, less than 10%. Okay, so yeah, so that's the solution of the prisoner permutation problem.